Picture this. You're on a walk in the woods, autumn time. You spot this decaying log, and it's just covered in these tiny, inverted, pear-shaped fungi.
Yeah, and they look totally normal, right?
Yeah.
Just unassuming little bumps on the wood.
Exactly. But to me, they look like, well, biological smoke grenades just waiting to go off.
Mhm.
So today we are doing a deep dive into a stack of recent botanical journals, some fluid dynamics papers, and aerosol science studies.
They're a pretty wild mix of sources for a mushroom, honestly.
All right. We are unpacking this tiny taxonomic rebel, Apioperdon pyriforme, which is the stump puffball. Our mission here is to explore its biomechanics and figure out how its chemistry is actually, solving modern physics problems.
Yeah, and those biological smoke grenades, they actually use this passive bellows system. So as the fungus matures, this little hole called an ostiole opens up at the very top.
Okay, like a little chimney.
Yeah, basically. And the outer skin, the peridium, it gets incredibly flexible. So when a raindrop hits that skin, it compresses the air inside and physically punches millions of spores out through the top.
Wait, seriously, it leaves reproduction up to like a random raindrop. I mean, that feels like a massive evolutionary gamble. Why not just actively catapult them into the wind like a normal mushroom?
I mean, it does seem like a gamble, sure. But then you look at the fluid dynamics. When millions of spores eject all at once, they drag the surrounding air with them.
Oh, so they create their own breeze.
Exactly. Physicists call it a cooperative wind. By moving together as this dense cloud, they mobilize the air into a continuous jet. It carries the spores like 20 times further than a single spore could drift on its own.
That's wild. But how does a cloud of dust stay together like that? Wouldn't it just, hit a leaf and completely scatter?
Well, no, because the moving cloud generates its own microcurrents. The fast-moving spores create a low-pressure zone right at the front of the cloud.
Oh, wow.
Yeah, and that pressure gradient literally pulls the rest of the spores forward. It allows the whole jet to bend and just seamlessly steer around obstacles.
So they're aerodynamically perfect, basically. Does that uniformity have uses outside the forest, though? Like, how does a rotting wood fungus end up in high-tech optical aerosol calibration labs?
It all comes down to their microscopic chemistry. The spores are almost perfectly spherical, and they're virtually identical in size. We're talking consistently between 3.3 and 3.6 micrometers.
That's incredibly precise for nature.
Right, but more importantly, they are coated in these specialized proteins called hydrophobins, and these proteins aggressively repel moisture.
Okay, but how does repelling water make them useful for calibrating, like, expensive lab sensors?
So because those hydrophobin proteins repel moisture so intensely, they generate static friction against the air. It's like rubbing a balloon on your hair.
Oh, so it creates a static charge.
Yeah, it's an electric shield around each individual spore, so they constantly bounce off each other instead of clumping. In aerosol science, expensive synthetic particles often clump up and ruin the data.
Wait, so scientists just use the mushroom instead?
Literally, yes. They can just squeeze a puffball directly into a multi-thousand-dollar sensor to calibrate it. You get perfectly uniform, totally unclumpable particles.
That is amazing. But if these highly charged water-repelling spores resist clumping that well in a lab setting, what happens if that unclumpable dust interacts with the human body?
Well, on the outside of the body, it's actually incredibly useful. Historically, these spores were packed into wounds to stop bleeding.
Oh, like a natural coagulant.
Kind of.
Yeah.
But it's important to separate the mechanics from the chemistry here. The blood clots, purely because of the physical structure. The massive surface area of millions of tiny, highly absorbent spheres acts like a microscopic sponge.
I get it. It physically forces coagulation. It's like nature's styptic pencil for a cut in the woods.
Right, exactly. But separately, on a chemical level, the stump puffball is loaded with phenols and flavonoids.
Which are good things, right?
Yeah, those are the protective antioxidant compounds you would find in high-end skincare or, commercial food preservatives. They aid in tissue protection. However, you absolutely never want to inhale this dust.
Let me guess. Because of that same anti-pumping mechanism.
Precisely. If those resilient spores get into your respiratory system, it triggers lycoperdinosis.
That sounds bad.
It is. Because the spores won't break down or clump together, your immune system essentially panics, trying to clear out millions of tiny, indestructible spheres. It leads to severe lung inflammation.
It really makes you wonder, if a common puffball already perfected anti-clumping aerosol technology millions of years ago, what other human engineering problems, like designing better drug delivery inhalers or preventing ice buildup on airplane wings, could be solved just by looking at the right fungus?